In this video, we'll be focusing on soil pH. Before we go any further though, let's break down what pH actually is. Every aqueous solution in nature is derived from water, or at least has water in it. Water is H2O, and it's not perfectly stable. A small fraction of water molecules continuously separate into two components, hydrogen ions being positive and hydroxyl ions being negative. You don't need to know the chemistry behind the pH scale. Just remember, a pH of 7 is neutral, less than 7 is acidic, above 7 is alkaline. One more thing, the pH scale is logarithmic, meaning that a pH of 8 is 10 times more alkaline than a pH of 7. So why is pH so important? Well, soil pH directly controls the availability, or more specifically, the solubility of plant nutrients. The nutrient availability sweet spot lies between a pH of 6 to 6.8, shown here with the pH on the x-axis and general availability on the y-axis. Most macro and micronutrients are available to the plant root within this range, if also the concentration is optimum as well. If the soil pH extends beyond either direction of this sweet spot, then nutrients can become potentially precipitated out and become not as available to the crop, causing a concern for crop production. Now let's look at some aggregated data sets from 3 vastly different regions of the state: the San Joaquin Valley, the Central Coast, and the Imperial Valley of the Lower Desert. With pH on the x-axis and the density of samples on the y-axis, here are the soil pH distribution curves for the San Joaquin Valley, the Central Coast, and the Imperial Valley. All 3 graphs include a green vertical line drawn at neutral 7. Do you notice a pattern here? Yes, all 3 data sets show a prevalence of soil alkalinity. So why would that be? One reason, due to our low precipitation rates, there's little to no leaching of basic cations such as calcium, magnesium, or potassium. Another reason would be the parent material of our soils out here are alkaline in nature. And the third reason would be irrigation water, for the most part, can be alkaline, especially from wells or sources like the Colorado River. So remember that sweet spot on pH and nutrient availability? The macronutrient phosphorus should really be the poster child example of how a nutrient gets tied up in alkaline pH. To showcase this, let's go back to our aggregate data sets, this time reflecting soil phosphorus levels on the y-axis, plotted against increments of soil pH on the x-axis. Notice that all 3 regions of soil phosphorus values are always the highest in the lower soil pH categories. Okay, what about those acid soils in this alkaline environment? From those pH distribution curves I showed you, 36% of the San Joaquin Valley soils are acidic. 35% of the coastal soils are below 7, but only 3% of the Imperial Valley soils drop below 7. I believe that the first 2 geographic examples, acidic soils, exist because of ammoniacal fertilizer usage over time. When the ammonia ions from an ammonia-related fertilizer oxidize to nitrite, before it gets to nitrate, 2 hydrogen ions are released, leading to potential soil acidity. So even if we're in an arid area, have alkaline-related parent material, soils still can become acidic enough for blueberries, particularly on the east side of the San Joaquin Valley, where, as you may recall from my first video, the soils are sandier and have lower CEC values. And speaking of CEC, a major mea culpa. In that first video, I had shown you this chart regarding CEC and soil texture, but there was a glaring error showing sandy sand, which doesn't exist, instead of sandy loam. Profuse apologies. I'm a tad embarrassed that happened, but it's a good lead into my final point of this video. There is a noticeable buffering effect on pH with higher CEC soils, such that soils with higher CEC values usually have higher pH values as well. Higher CEC means there's more room on the soil colloids to store those basic cations, and hence there's more competition to fight off those acidifying hydrogen ions. So let's look at our 3 regions of aggregate data, this time with CEC plotted against pH. CEC on the x-axis and pH on the y-axis. Here's the San Joaquin Valley, here's the coastal, but actually with the Imperial Valley soils, that trend is really not there. I contend it's because the quality of irrigation water, which is primarily from the Colorado River, is more alkaline in nature, and there's also fewer sandier soils in that area. If you stuck with me this far, you've been a great student. Join me next time on California Soil and Water, where we'll cover another agronomic topic.